Hey guys, this is Mr. Bennett, and this is Unit 15, video number 2. We're going to talk about concentrations. So the first thing we need to do is we need to define what a concentration is. Concentration is the amount of solute dissolved in a given amount of solvent. And it turns out there are 4 different ways that we can measure concentration or express the concentration of a solution. The first way is known as the molarity, and the symbol for molarity is a capital M. This is the reason why I told you not to use capital M as your symbol for moles, because capital M is already taken by molarity. Molarity, though, actually does have to do with moles, hence the reason why it's molarity. It is the moles of solute per liter of solution. So really, molarity, you could also think of it as being moles per liter. That's kind of the fancy way of looking at the units, but we simply take this and we write it as a capital M. They mean the same thing. Okay? So formula-wise, the formula for determining the molarity of a solution is simply the molarity equals number of moles of solute divided by number of liters of solution. Okay, very easy. Think of it as, based on our last couple units, you have 3 variables. You have the molarity, you have the moles, and you have the liters. In a typical problem, they're going to give you 2 out of 3, and you'll solve for the third. So let's look at 2 different examples, 2 different ways that we can do that. We can get 2 variables and solve for the third. So in the first one, our first example here, it says determine the molarity of a 3-liter solution. So it's all about the units. The units tell us where to plug it in, so in this case it's 3 liters, which means it's going to get plugged in on the bottom. And then it says molarity of a 3-liter solution that contains 0.75 moles of calcium chloride. So moles means that's going to go on top. So, and again it says determine the molarity, so I know that my molarity is what I'm solving for. It is my x, essentially. So molarity equals the number of moles, which is 0.75 moles, divided by the number of liters, which is 3 liters, and then think of it as, math-wise, we can think of this as 75 divided by 3, or so if you had 75 cents, that would be 3 quarters. So divided by 3, it's going to be 1 quarter, or 25. Put my decimal and my 0 back in, so 0.25, and then my units are moles per liter. But I told you moles per liter is really the same thing as molarity. So I can rewrite this as 0.25 molar, and we want to know the substance, so I'm going to write calcium chloride. Okay, so they gave us the moles, they gave us the liters, we solved for molarity. Here's another example of how they could do it. How many moles, so moles are going to be our x, are in 3 liters, so there's our volume, of a 2 molar solution. So 2 molar is going to be our molarity, we're going to write that first. So 2 molar equals the number of moles, that'll be our x, over 3 liters. Okay, so to solve this one, I want to get x by itself. X is being divided by 3 liters, so I can simply multiply this side by 3 liters, multiply this side by 3 liters, and that's going to give me x equals, because these guys cancel out, right? X is all by itself, equals 3 liters times 2 molar. But remember, molar is really the same thing as moles per liter, so this is 3 liters times 2 moles per liter. Okay, unit-wise, liters divided by liters, they're going to cancel out, so I'm going to be left with 3 times 2, which would be 6 moles. And that's my answer. Now there is a third type of problem they could do. They could give you molarity, they could give you moles, and you solve for liters. That's just the only other way they can do it. Okay, so that's molarity. That's our first way of looking at concentrations. Let's go on to number 2. So number 2 way of describing concentrations is known as parts per million. And the symbol for this is simply ppm, hence parts per million. That's the number of solute particles per million particles of solvent. It's typically used for very dilute solutions, so things where there's barely anything dissolved in it. And the formula is pretty straightforward. It's grams of solute divided by grams of solvent, and then you take that and you multiply it times 1,000,000. hence the parts per million. So you got to multiply by a million. Okay, so let's look at an example here. We have 55 grams of solute, so that's grams of solute goes on top. So I say 55 grams divided by 1,000 grams of solvent. Now notice my units work fine here, meaning they gave me grams. I need grams to plug it in. They also gave me grams of solvent. I need grams of solvent to plug it in. So I can plug these directly in because they have the right units. They're both in grams. So on the bottom I'm going to plug in that 1,000 grams, and then I need to multiply it times a million. Okay, and now we can do some reducing. For instance, we're dividing by 1,000, we're multiplying times a million. So I can get rid of 1, 2, 3 zeros here, 1, 2, 3 zeros here, and I'm left with 55 times 1,000, which means I have 55,000 parts per million. Pretty easy. Just got to remember that whole grams over grams times a million. Now the third way we can do concentrations is actually a really common way. We see this a lot. It's called grams per liter. As far as abbreviations, well, or symbols, or whatever you want to call it would just be G/L. Pretty easy. So grams of solute per liter of solvent. It's a very common method that's used in many places. For example, it's used a lot in liquid medications. So if you buy liquid medications from the store, say like liquid Tylenol, it's often described in terms of grams per liter, but these are very big measurements. So typically with medications, they scale it down into the millis. So it'll be like milligrams per milliliter. Let's give you an example here. 1,500 milliliters of water dissolves in 3 grams of sugar. What is the concentration in grams per liter? Now this is a good example for one reason, well, a couple reasons. First reason is our units need to match what we're asking for. So if we're asking for, in this case, grams per liter, right, then that means when we actually plug in our numbers and divide, we need to have grams and liters. So if we look over here, yes, we have grams. But if we look right here, we have milliliters. So before we can use this, we're going to have to convert it to liters. And that means we got to think back to the beginning of the year when we were converting from one, essentially part of the SI unit, so going from the scale of liters to millis or kilos or whatever that may be. So we're going to use our KBM tool. So KBM, remember K stands for kilo, B stands for base unit, things like grams, liters, meters, and then M stands for milli. We also know that 1 kilo is equal to 1,000 base units, and we know 1 base unit is equal to 1,000 millis. So in this case, we have 1,500 milliliters. Okay, this is dimensional analysis, so we need a dot, at least one dot and one line. How many do we need? Well, we have millis, right? And we need to get to liters, which is the base unit, so that's one step or one movement left, so simply just one dot line. Now we have milliliters right now, we want to get rid of those, so I'm going to put milliliters on the bottom. I know I want to get to liters, so I'll put liters on top, and then if I look at my numbers over here, it's one base unit, or 1 liter, for every 1,000 millis. So easy as that. Now math-wise, we're simply going to, let's cancel out 2 zeros here, 2 zeros here, we're left with 15 over 10. If I divide those both by 5 or reduce it by 5, I'm going to get 3 over 2 liters. Okay, now I have liters, so I can plug that into my equation, which is simply grams per liter. Now they say we have 3 grams of sugar, so I do 3 grams divided by 3 over 2 liters. Okay, now you might look at this and say, oh my gosh, we're dividing by a fraction, this is horrible. But if you remember your algebra, or math, remember when we divide by a fraction, that's the same thing as multiplying by the reciprocal. So in other words, I can say 3, again 3 divided by 3 halves is the same thing as 3 times 2 over 3, because I simply took the 3 halves and I flipped it, right? And our units are grams per liter. Okay, and so for that, all I have to do is reduce, boom boom, 3 divided by 3, that's going to become 1 and 1. So it's 1 times 2 divided by 1, also known as 2 grams per liter. Okay, so let's talk about our fourth and final type or method for expressing concentration called percent composition. It's the solutes portion of a solution. Formula-wise, it's very similar to parts per million because you're going to be using grams. So it's grams of solute over grams of solution. And then because it's a percent, we're going to multiply it times 100%. Now, if you're having trouble remembering, okay, it's solute and solution and stuff like that, think of it in terms of when you take a test and you're trying to figure out what your percent is, right? So if you take a test, you want to look at your number that you got correct over the total number of problems, right? And then you multiply it times 100%. Well, that means in this case, what you got correct, or the part of the whole test that you want to look at, the correct part, is equivalent to the part of the solution we want to look at, which is the solute. And then the total, because we're comparing what we got correct to the total number of problems, is like what we're when we're comparing the amount of solute to the total amount of solution. Okay, so let's do an example here. We've got 450 grams of sodium chloride dissolved in water to create a solution with a total mass of 1 kilogram. Good stuff. This is going to be our solute. We're going to plug it in on top. But notice we've got a problem again. They gave us the total mass in kilograms, but we need it in grams. So before we can use this, we're going to have to take our kilograms and we're going to have to turn them into grams. Based on kbm, that means that we have kilos. We want to get to base units, so we got to go one step. Okay, and remember, it's 1 kilo equals 1,000 base units. Okay, and actually, it turns out I'm not going to have to do dimensional analysis because they gave me 1 kilogram. I know 1 kilogram is equal to 1,000 grams, so I'm just going to write 1 kilogram equals 1,000 grams. Okay, and if you're saying like, what are you doing? What are you talking about? Again, in order to determine percent composition, you must have them in grams over grams. They gave us grams and kilograms, so we had to convert these kilograms to grams before we can use them. So now let's plug everything in. We've got our 450 grams of sodium chloride, that's our solute, so I'm going to put that on top, divided by, they told us 1 kilogram of solution, but we converted that to grams, so that's going to be 1,000 grams, and then this is percent composition, so I'm going to multiply it times 100%. Okay, and we can do some reducing. So first of all, I can take this 0 and this 0, kill those, get rid of those, and then I have 2 zeros on the bottom, meaning I'm dividing by 100, and I'm also multiplying times 100. So these are going to cancel out. This will turn into 1, this will turn into 1, so I'm left with 45 divided by 1 times 1, or 45%. Alright, that's it for these notes. Make sure you complete the whisk, and if you're doing this after Friday, then have a great spring break, and I'll see you guys when you get back. Stay safe.